Good day, everybody. Before we start with my presentation, I would like to introduce you to my country, that is Malaysia, where it is a little bit closer to Indonesia and Singapore. And if you look at it, we are at the peninsular side, UTHM. University Tun Nasional Malaysia is at the peninsular side, and we are a little bit southern to the peninsula. And we have new campus, that is Pago, and you can see the old building there on your left, bottom below on the right, left, and while on the right you can see that this is a new building that we have at our main campus. And again, that is the new facilities at the campus, and this is the map of UTHM. The old campus is at the far bottom corner, while at the top part is the new facilities, I think installed last 10 years. And now we have new campus in Pago. You can see that this is the map of the new campus. It consists of a few universities there. We are part of it, called as Hub Educations, where a lot of 5 universities are at this area. And this is our iconic building in UTHM, the library, the mosque, and the convocation hall. And we very much as engineering university, where we have a lot of engineering programs such as aeronautics. We have train also. We have all the ordinary engineering faculty like electricals, mechanicals, and civil engineer. And I would like to invite you to our own conference called Schematic 2019. Will be held in August, 14 to 15 August. It will be in my home state, Malacca City. So I would like to invite every one of you to participate in this conference. It will be nice to meet you all there. Now we go to our presentation, my presentations, that is second manipulations, laser irradiation to polymers. And that is basically the theme of my work since PhD. And now we get new things out of the laser irradiation to polymers. Then the title for today's talk is Polystyrene Embedded Silver Nanoparticle as Heavy Metal Removal in Wastewater Remediation Applications. Okay, the motivations of us in doing this research is originated from photolithography, where you can see that by irradiations polymer material, that we call it polymer resist materials or photoresist substance, we can get two types of polymer behaviors. That's either they become positive resist, where you can see that the part that been shined can become breaking up their bonds and easy to be removed, while the part that's become hardened, it's become negative resist, they will become cross-linking or binding together. And therefore, with these two features of the polymer, we can fabricate the integrated circuits for fabricating our devices, which as we talk now, the line that been fabricated, the line features that been fabricated are going down below to 20 nanometers. Imagine that with this kind of technology, we managed to have all these gadget, all these electronic instrument. we have computers and phones from this simple way of manipulating. So the most important part as research, if we understand what is research about, is about how to manipulate materials. So the keywords in doing research is you need to understand what is the thing that you manipulate. So in this sense, polymer is being manipulated by light that interact with the polymer, change the chemical structures. Either they easily become dissolved, or they become cross-linking, or they get bind together and become hardened. That we call it as negative polymerization. So why we are motivated to do research? Imagine that we are trying to create faster computers. So how can we do that? Okay, we need to really understand our materials, especially understanding the polymer and why they started to create chemically transform into new materials. And we, for my research group, we are interested in what kind of the new material that been fabricated during the laser or electron beam irradiated to the polymerization. So this is the big question for us. What is happening during the fabrication or post-curing or post-fabrications? And if these materials is able to make us tune the polymer to become into three basic conditions of material, that is insulator, semiconductor, or conductor. So this is the main question for us. Can we have a polymer that can be tuned into these three conditions? Okay, so that is our motivations. Therefore, we need to understand what is polymers. Polymers are identical units. They are bond each other into long chains, and they can be categorized as thermoplastics and thermosetting. And thermoplastic are organic that can be melted by heat, while thermosetting is polymer that become irreversible hardened upon being cured. So we have thermoplastic that can be called as photoresist materials that react with photon. The most well known is polymethyl methacrylate, is PMMA, or polystyrene, and then LDPE, and other type of polymer. And why we are looking into polymer, as you know, that we have recently have a flexible display that can be either you can make it in any form that you like. That is the wonderful thing about polymer, because they are lightweight, flexible, easy to process, and of course one particular interesting material things is that it is resistant to corrosions. So we have something that can be eliminate the corrosion problem. Okay, so in our case we are interested with polystyrene, because polystyrene is the basic unit of polymer. We have C8H8 and N repeated units, the C8 and H8. Then it consists of very limited elements, that is only carbon and hydrogens. Besides, probably they will be interacting with oxygens in the air. But nevertheless, polystyrene can be in three forms: isostatic, where you have your benzene ring on one side; symbiotic, it alternated of the benzene ring; and the aliphatic, that is not really having any kind of structured orientations of the benzene rings. Even the polystyrene, you can synthesize it to become nanospheres, very small, and then if we able to manipulate this polystyrene, probably it will be look like this. We have certain kind of hexagonal honeycomb ring that can be fabricated. I have done this during my PhD. So basically, using polystyrene is very low cost. It is simple molecules. So whenever we make any changes to this, we understand that only carbon and hydrogen is involved. And of course, it also have good electrical properties, which is usually they are insulator, low water absorption, and excellent in color range. So now, once we know the polystyrene, we need to know what is the basic problem at the nano regime. The first thing is precise positions. So why we need to precise position material? Because such as nanocora, where we can get free energy from electron vibrations, and making the interconnections. Okay, once you fabricate, you need to create the interconnections, and of course later on mass production for creating devices. Okay, mass production. If you can't mass produce it, it will be a drawback for your research. And the fourth is functional devices, meaning that imagine that every particular change in the molecule change can be used for certain type of purposes, such as you can turn it to become diodes or something like that. Okay, this is some research done by people. You can see that people try to modify the polymer to become a flap of the wing, okay? And now the polymer can be doped. Okay, so we can fabricate this kind of devices by using different kind of radiations to this polymer, and yet we have some part become a little bit much stronger, some part will become a little much thin and lighter. So that is the thing that we try to look at. Even polystyrene, they found that it can be used to emit white light. Okay, this is done by a Korean guy, Young-Hyun Kim and Ji-Hoon Kim. Okay, so these people, they look into polystyrene for their research, just like us. So now, when we realize this, we know that we are interested with polystyrene, and we try to dope this polystyrene with nanoparticles such as silver. So silver nanoparticles is very interesting material also, because it's been used for nanoelectronic optical filters, electromagnetic interference shieldings, microwave absorbance, surface environment scatterings, and of course in our work it can become as heavy metal absorbers. So the theme of our work is synthesis of silver nanoparticles. We can change into other nanoparticles. We can put into the polystyrene to create a new composites, that these new composites can be easily deposited to become into like nanoparticles, okay, nanospheres. And when we put it into the substrate on silicons, we can bombard it with laser, and therefore when we bombard it with laser, we want to know which part of this polystyrene able to be modified. And this is some of the equipment that we use: FISAMs, AFM, that is for morphology, For chemical, we use FTIR and Raman spectroscopy, and for structural analysis, we use XRD, and for optical properties, we use UVVs and VNA. This is some of the research that we do, and I only will be explaining you about certain part of the device. Okay, the result of the device. Okay, this is the result for UVVs visible, UVVs for synthesized argentum nanoparticles. So we can see that we managed to calculate the argentum nanoparticle is about 15 to 8 nanometers. And this is the image of the polystyrene that we synthesize it in nanospheres like structure. You can see that some of the nanoparticles, especially silver nanoparticles, either it's get into the polystyrene, okay, or when the concentration is higher, they started to be seen on the surface, and when they are much more, you can see that the silver nanoparticles like cover up the polystyrene. And this is when we try to laser bombardment of polystyrene, okay, just polystyrene. You can see that the different in colors only, while the shapes and the image of the size doesn't change much. So that is a little bit interesting to look at it. Okay, I will try to explain to you later. So this result is the FTIR for polystyrene argentum nanoparticle composite. And when you see that, imagine that this is your polystyrene, and between it, as there is some part of polystyrene that able to vibrate, so we can get this kind of spike. But when you dope it nanoparticles, some of the vibrations has been losing. We lost the signal here, meaning that the molecular change is now restricted from vibrated. And of course, you can see that at this area also, some of the nanoparticles started to prohibit the polystyrene molecule to vibrate. And if we investigate it with Raman spectroscopy of the polystyrene argentum nanoparticles, we can see that this is the below part is just polystyrene. You can see that the D band and G band doesn't show much at this. The D band and G band is showing off the molecule restructuring. So when the nanocomposite of argentum nanoparticles, okay, when we put nanoparticle inside it, okay, we can see that it's already changed the polystyrene. So by doping also, by just doping, the nanoparticle seems to make a clear presence that they make the polystyrene to somehow restructure themselves. Now, if we irradiate it, then you see that if we irradiate it, if we look at this band, okay, we can see that some part of the peak will be lost, reappeared and disappeared at the depending on the dosage of laser. So the longer the laser you expose to polystyrene, the polystyrene somehow like change, and then it change a bit, change again and change again like that. So you can see that this peak, okay, if you look at the left part peak, when you expose it to B is 20 minutes, okay, 20 minutes of irradiation. You can see the peak, okay, a little bit clear there, and then start to disappear at C at 40 minutes and reappeared again at 40, 50 and 60. So at the 30 minutes it disappeared. So this kind of understanding that perhaps we can use laser irradiations to tune materials. And again you can see that some of the peak here at the band of 1492, you can see here is quite big and suddenly it disappears at 50 minutes and 60 minutes is reappear again, meaning that this actively restructuring of polystyrene is the thing that very much interests us. Now, okay, if we put nanoparticles into the polystyrenes and we do the same by laser irradiations, okay, this is for 1:8 ratio. 1 is polystyrene and 8 is nanoparticles, and you can see that we have some kind of fluctuation also, okay, especially you look at this blue line, we have disappearance of the peak there. So this is interesting because somehow by laser irradiations we are tuning the properties of polystyrenes. And in fact, when you look at the XRD, okay, this is 20 minutes, no obvious of restructuring, but at 30 minutes you can see that we have this signal at about 58 like that, and then it suddenly the peak reappeared on the left side, and then the peak have two peak now at 50 minutes, and at 60 minutes you got two clear peak there, okay, and this is just for polystyrene. Now if we put argentum nanoparticles, we can see that they are very much interesting. You can see that for polystyrenes they are not arranged at all, but after 20 minutes, okay, of irradiations, okay, B, C and D is polystyrene argentum result of nanocomposite, meaning that just doping the nanoparticle into the polystyrene already make the different arrangement. Now if we laser it, okay, you can see that this is just polystyrene. Now with nanoparticles you can see that it just moved toward this side, and at this part, okay, at the 60 minutes we are confirmed getting the graphite and the diamond-like carbon structure, meaning that by looking into the ID and IG ratio we can see that the polystyrene with nanoparticle can be tuned into fabricating diamond-like carbon. So that is the interesting part, and it is confirmed by Raman spectroscopy. At the 60 minutes you can see that we got the D and G bands seem like level, meaning that they are really crystallized. So there are huge potential for this kind of tuning. So just like diamond like carbon, okay, that can be used for MEM application for electronic device. That is what we are looking about, meaning that I didn't have the time to report the energy gap, and we did also with gamma ray, and we found that the energy gaps can be tuned based on the dosage. This is laser irradiation, this is gamma irradiations, and you can see it's behave like about the same, meaning that we can tune these materials towards at the end maybe becoming diamond like carbon. And recently, okay, there are a few research that focusing on a diamond battery that can be created from nuclear waste, and the battery can last about 5,000 years. Just imagine that we have nuclear waste, we coat with diamonds, and then we got battery. Now here it's been in June 1st, 2018, the Russians already create this type of battery, and they reported it at 10 times more power. Okay, imagine that. This is the structure, meaning that if we can coat our radioactive materials by diamond cell that we fabricated with laser irradiation to polystyrene, we can create this battery in the future. That is our future work. But for these presentations, I just like to draw you a very simple research done by our degree students. This is we use polystyrene, waste polystyrene. We dilute it with tetrahydrofurans and with nanoprecipitations to create it become as small nanospheres. Okay, that can be from 1 micron to 5 microns. Okay, even we can make it less, depend on our style of doing it. And if we can dope this polystyrene with silver nanoparticles, and of course when there are more concentrations of silver nanoparticle, you can see a lot of spike, whilst when you have less, you will see much more smooth surface because of the polystyrene. So why we are looking into this kind of work? Because it is very simple. We use waste materials, and even silver nanoparticles is very easy to fabricate by biology technique, like we're using plants to create the nanoparticles. And of course we can use chemical reductions to create nanoparticles. And if we go back to our previous slide, seems that if we put the nanoparticles into the polystyrene, it's already changed the chemical structures. And of course that nanoparticles and that nanospheres of polystyrenes, they have a very high surface to volume ratio, which is a very good candidate to become as adsorber. Okay, as adsorber. Okay, now with doping of silver nanoparticle, the polystyrene is already having slight changes, and if we irradiate it, so that will be our future research. And we also managed to prove that it can become as insulator. We can also prove that it can become a semiconductor. This is part of our research, ongoing research. And now we are also looking into bimetallic dopants. If we put bimetallic into the polystyrene, what will happen during the dopings? Okay, and during when we laser irradiate it. So very huge potential for these kind of works. So meaning that we would like to investigate what is the possible interactions with other particles, especially for silver with polystyrenes, okay, titanium with polystyrenes, and some other nanoparticle, metal nanoparticles put dope into the polystyrene. And of course for this research we see that it can create higher absorption rate, especially using for the use of removal of heavy metals from wastewater. So we fabricate the synthetic wastewaters, okay, and into the distilled water, and we dope polystyrene with 7 nanoparticle first, and then immerse into the synthetic wastewater. And we want to investigate how much can be the zinc can be absorbed. Of course, again, we look at what is the thing that we try to manipulate. So we try to manipulate how much time it takes for the zinc to be absorbed by the polystyrene argentum nanoparticles, and what kind of pH that the reactions are much more higher, much higher. So for pH, we can see that this is polystyrene with argentum nanoparticles, okay, and the ratio is 1 to 3 and 1 to 5. The left is 1.3, 1 to 3, and the right is 1.5, 1 to 5, okay. And this is the weight of the concentration of zinc in the synthetic wastewater. So it means that they are optimized at pH 5, meaning that both of it can be used as effective heavy metal absorber, okay. And it seems 1 to 3 and 1 to 5 ratio, they are giving the same results. Within the pH 5, we can get 100% of zinc will be absorbed by polystyrene argentum nanoparticles. And then if we look at the contact time, okay, contact time meaning that we try to see how fast that the zinc can be absorbed by polystyrene argentum nanoparticles, okay, or polystyrene argentum nanocomposites. And we can see from the left and to the right is again 1 to 3 ratio for argentum compared to polystyrenes, and the right side 1 to 5 polystyrene is doped with argentum nanoparticles. And we can see that within the first minutes, okay, of the contact time, nearly 40 to 60% of zinc can be considered as heavy metal have been successfully absorbed by these polystyrene argentum nanocomposites, and nearly 100% within 50 minutes. So meaning that it is a viable technique that we can put nanoparticles into polystyrene and can become as heavy metal absorber. And this is the conclusions. Of course, I would like to look at you that the UV spectrum confirmed the formations of nanoparticles. The effect of silver nanoparticle incorporated into the polystyrene, you can see that it is obvious in PSAM, AFM, XRD, FDR, Raman and UV spectrum. In fact, we calculate the energy band gap. I would like to give that data, but it's we have limited time. XRD showing that the data prove that the polystyrene transform into various unknown material yet for us now. As far as we know, it can become as diamond-like carbons during longer exposures. And for the Raman spectroscopy, we confirm that the D band and G band ratio, ID over IG ratio, is nearly about one that showing it's become as diamond-like carbon. So it's very interesting. And then of course the things that we want to highlight here is meaning that we are able to tune the chemical and structural morphology, opticals and thermals and electrical properties of these materials, especially polystyrene. Meaning that if once we can tune these materials, it opens up so many possible applications. And then I would like to draw you to this image, okay, where we are using laser irradiations. During my PhD, I use electron beam irradiation to polystyrene, and we are looking also into ultraviolet light. How does it change the polystyrene? And of course, we are also interested in other polymer like polyaniline and PMMA. I have about 8 PhD students. They are all doing about polyaniline and PMMA and polystyrene doped with nanoparticles, and either we laser irradiate it and we try to look at how we are able to create it to become as insulator or semiconductor or conductor materials. And of course, meaning that we can tune the materials. Of course, when we tune the material, we tune their energy band gap. Therefore, it can be useful for solar cells and light emitting materials. This is done by one of my research students. And of course, it can become as coating materials. So especially for the diamond-like carbons, we like to investigate how the coating of polystyrene and laser bombarded with laser, and we want to investigate how it prevents corrosions to materials. That will be another future research. And of course, now once we can make it as diamond-like carbon or semiconductor, we want to look at it as conductor material or superconductor material. And of course, for this small research done by my degree students, heavy metal absorbers, now it's become clearly seen it is possible for us to use this technique as a wastewater remediation technology. Okay, and one of my PhD students is now not only try to use polystyrene doped with other metal particles, and we try to create a surface that can be used to attach drug, that can be used for drug delivery systems or as antibacterial materials. This is part of the published paper. The work done here much more by Jibrin Al-Haji Yabagi from Nigeria, and for the wastewater it's done by Begna de Cruz. And with that, I would like to thank you everybody for giving me your attention to my talk. Thank you very much.